must have noticed that in case of cold drinks, the container is cylindrical, but in case of juice or milk, the same quantity is rectangular in shape. Why do we decide certain shape to be cylindrical, certain shapes to be rectangular? What is the main idea behind it? At the same time, you would see some cylindrical shapes for the same amount, for the same volume, 250 ml, it would be a lot shorter and a lot wider. The radius is much higher and the height is smaller. How do we decide what would be the exact height or radius of a cylindrical shape, or why would it be cylindrical shape, or why it would be rectangular shape? Well, it deals mainly with how companies think it's the best for the particular product, and we use differential calculus and we call it optimization of area or volume. How do we find the perfect situation where this is the height we should use for maximizing the volume or area, or minimizing the area or volume? Because there would be certain restrictions. For example, there could be a restriction: you have to make sure that the volume is 250 ml. It is fixed. So this is the restriction that is given the volume must be 250 ml, and you have to maximize the height or minimize the height. So what would be the minimum height for that container so that it can be manufactured uh, pretty efficiently? One reason for cold drinks to be cylindrical in shape is because it's easier to hold, because when we buy cold drinks, we usually instantly consume it. But in case of milk or in case of juice, what we do, we usually store it in the refrigerator, and it is easier to store if it's rectangular, because that way space is not wasted. Because if it is circular, you would see some space is wasted. At the same time, in case of uh, canned food, it's usually shorter, and the radius, although the shape is cylindrical, the radius is wider, because in that case you don't have to dig very deep with the spoon, and that way the height would be smaller. It's easier to eat. So these are decisions that companies make about optimizing the product. Now, this is what we do first of all. The first thing that we do, step one, is we need an expression. We need an expression of the area, or if you're optimizing the volume, or of the volume, in terms of one volume on one variable, only one unknown variable. This is very, very important. What does it mean? It means, for example, we have the volume of a cylinder. It is pi r square h. Both radius is a variable and height is a variable. We need to make sure there is only one variable, only one unknown variable, either radius or height. The same with a cone, 1/3 pi r square h. So we have to make sure that the area or volume, for optimizing it, for the uh, product to be absolutely efficient economically, and also uh, in terms of space, in terms of usability, that is very, very important. After that has been done, when we have only one unknown variable, the next step would be to do the actual calculus. In this, what we do, the rate of change, either in case of maxima, meaning maximum, plural of maximum is maxima, or minimum, if when we're optimizing for the minimum space required, the rate of change must be zero. Must be zero. Suppose we have volume expressed as radius, then dv by dr, then that should be equal to 0. And when you do that, in order to maximize the rate, that should give you the radius for which this situation would be uh, usable. So that is the next step where you do that. After that, you have to find the maximum volume, or the minimum volume, or the maximum area, or the minimum area. So you have to put the value. In this particular example, if it's the radius or if it's the height, you have to plug it in. So find the maximum or the minimum volume that you can actually produce for that particular product. It can also be area if you're talking about flat space. It depends on what type of product the company is manufacturing. And the final step, because since you have to go into manufacturing, you have to make sure it is actually correct. So for that, we have to verify that it is indeed maximum or minimum for that particular value. So for that, we do the second derivative. This is known as the second derivative rule. Second derivative rule. So the second derivative works like that. The second derivative of dy by dx is d2y by dx squared. That means if you do the derivative of y, you get dy by dx, known as the first derivative. Now if you take this again and do another derivative, that means d by dx of dy by dx, that is the second derivative. We write it as d2y by dx squared. So if you take the value and plug into the expression of the second derivative, and after that, if it is negative, in math we write negative as less than 0. If it is negative, then we can say that it is maximum. On the other hand, if we find the second derivative and we plug the value of x or r, whatever it is, and we get a positive value, then we have proved that it is a minimum value. So that's how it works. So remember, we have these steps. The first step is knowing the expression in terms of one unknown variable. The second step is making the maximum or minimum rate to 0. It could be dy by dx, it could be dv by dx, it could be dv by dr, dA by dr, and so on. And then we usually find the maximum or minimum value, and we also have to verify. Usually what we do, we verify before finding it to check whether we are in the right track or not. This is similar to the concept of coordinate geometry where we find the turning point. Remember this.